Welcome back. This is part 6 of the DoveBridge Technologies private cloud series. In the previous 2 episodes, we installed and configured OPNsense at our headquarters in DoveBridge. That setup was essential groundwork, and it's now complete. Today, we move on to deploying Active Directory domain services. Once finished, all future servers and client machines we install will become part of a connected corporate network. From this point onward, users will have network accounts, computers will join a domain, policies will be enforced automatically, and access will be centrally managed. Everything we build from here, file services, DFS namespaces, branch cache, group policies, will directly rely on this foundation. This is the part I find truly exciting every time. Before we touch a single server, I want to make sure you actually understand what we're about to build and why it works the way it does. So before we install anything, we're going to spend some time on the concepts, what Active Directory is, where it comes from, how it's structured, and why every decision in the design makes sense. If you walk away from this episode able to explain Active Directory to someone else, I did my job well. I'll also say this up front. Everything I'm sharing with you today comes from years of reading, experimenting, breaking things, and fixing them. There is no shortcut to that. If this material sparks something in you, and I hope it does, I genuinely encourage you to keep going after this course ends. Pick up a good book, build your own lab, go deeper. The professionals who truly master this technology are the ones who couldn't stop tinkering with it. The theory section will take roughly 25 minutes, but I promise it is worth your time. Do not skip the theory. After that, we get hands-on and install our first domain controller. Alright, let's start at the beginning. Imagine DoveBridge Technologies has 50 employees. Each one needs to log into a workstation, access files on a server, use a printer, maybe connect to a VPN. Without any centralized identity system, how do you manage that? The answer is badly. You'd create a local user account on every single machine for every single person. When someone joins the company, you touch every device. When someone leaves, you need to remember to remove their access everywhere. When you want to enforce a password policy, you configure it individually on every machine. When the security team asks who accessed which files yesterday, you have no coherent answer. This isn't a hypothetical. It's how small networks actually worked before directory services became standard. And it doesn't scale. At 50 users, it's painful. At 500, it's impossible. What you need is a single authoritative source of truth. A central place where you define who exists in the organization, what they're allowed to do, and what policies apply to their machines. A place where creating one account gives a person access to everything they're entitled to, and deleting that one account removes it all. That's what a directory service is. It's a structured database, optimized for reading, designed for fast lookups, that holds information about every object in your environment. Users, computers, groups, printers, services. It answers the fundamental question every enterprise network needs to answer. Who are you and what are you allowed to do? Now, a directory service is a concept. The question is how the rest of your network actually talks to it, and that's where LDAP comes in. LDAP stands for Lightweight Directory Access Protocol. It's an open, vendor-neutral standard that defines how applications and systems query and interact with a directory service. It doesn't tell you what software to run. It defines the language of the conversation. Whether a user's password is correct, it sends an LDAP query. When a file server needs to know which groups a user belongs to, it sends an LDAP query. When an application needs to look up someone's email address or department, it sends an LDAP query. LDAP is the universal language that systems use to ask the directory who someone is and what they have access to. LDAP organizes its data in a tree-like structure called the Directory Information Tree. Every object in that tree has a unique address called a distinguished name. If you've ever seen something like this, well, that's a distinguished name. It's a full address describing exactly where an object lives in the tree. The DC components represent the domain, the OU components represent the organizational unit path, and the CN is the object itself. LDAP is implemented by many different vendors and platforms. OpenLDAP is the most common open-source implementation. Many Linux environments use it directly. Apple has shipped LDAP-based directory services. Various cloud platforms have their own implementations. Microsoft's implementation is Active Directory. It takes LDAP as its foundation and builds an entire enterprise identity platform on top of it, adding Kerberos authentication, multi-master replication between domain controllers, group policy, site-aware topology, and much more. When we deploy Active Directory today, we're deploying a directory service that speaks LDAP. Every Windows machine on the DoveBridge network, every future Linux server, every application that supports LDAP authentication, all of it will be able to talk to the identity platform we're building. Let's talk about how Active Directory is structured. And we start at the top, with the forest. The forest is the outermost boundary of an Active Directory environment. Every Active Directory deployment has exactly one forest. The forest defines a common schema, the blueprint that describes what types of objects can exist and what attributes they can have. It defines a common configuration partition. And it defines a trust boundary. All domains within the same forest implicitly trust each other. Inside the forest, you have domains. A domain is the core administrative and security boundary. It has its own name, its own database of objects, its own policies, and its own domain controllers. Users authenticate to a domain. Computers join a domain. Group policies are applied within a domain. Large enterprises sometimes run multiple domains within a single forest, perhaps one domain per major subsidiary or one per geographic region. Those domains form a domain tree, and they can trust each other while remaining administratively separate. This is called a trust relationship. For our client, we don't need any of that complexity. We have one company, one IT team, and one set of policies. We use a single forest and a single domain, corp.dovebridge.tech. Both our DoveBridge headquarters and our Rotterdam branch office live in the same domain. They're separated by AD sites, not by domain boundaries, which keeps things simple and manageable. A domain controller is the server that hosts the Active Directory database and provides identity services to everything on the network. When a user logs in, a domain controller authenticates them. When a computer joins the domain, a domain controller processes that request. When a client needs to find a file server or printer, it queries a domain controller's DNS. The Active Directory database itself lives in a file called nltest.dit. The NT Directory Services database. This file contains every user, computer, group, and policy object in the domain. It's stored by default in the C drive system Windows folder /ntds on every domain controller, and it's replicated across all writable domain controllers automatically. This brings us to a critical design principle. You always need at least 2 domain controllers, not because it's best practice, because it's a hard requirement for a reliable environment. If you have one domain controller and it goes offline, nobody can log in. Nobody can authenticate. The entire environment stops working. With 2 domain controllers, either one can service authentication requests independently. They replicate changes to each other and stay in sync. Today we're building exactly that. 2 domain controllers at DoveBridge. And later in the course, we'll add read-only domain controllers at Rotterdam to serve the branch office without hosting a writable copy of the database. This is done for security reasons, since the server room in our Rotterdam branch will not be as secure as our headquarters server room. Let's talk about Active Directory and DNS. This is one of the most important things to understand before we start because it surprises people. Active Directory is completely dependent on DNS. ADDS uses DNS to locate domain controllers, replicate between them, and allow clients to find services. When a user logs in, their workstation sends a DNS query for special SRV records, service location records, that tell it which domain controllers are available and where to find them. Without working DNS, clients cannot find domain controllers cannot find each other, and Active Directory simply does not function. One thing worth knowing in 2026. Active Directory is IPv6 first. When both IPv4 and IPv6 are available on a network interface, Windows will prefer IPv6 for internal communication, including AD replication traffic. Kerberos authentication, and DNS queries between domain controllers. This is the default behavior, and it reflects where the industry has been heading for years. You can configure a preference for IPv4 through registry settings or group policy if your environment requires it, but for this course we are going with the default. IPv6 first. Our domain controllers are fully dual-stacked, and we will let Windows use IPv6 where it chooses. When we install the ADDS role on a Windows server, the software is there. But the domain doesn't exist yet. The step that actually creates the domain is called promotion. Promoting a server to a domain controller means running a configuration process that initializes the Active Directory database, sets up DNS, creates the sysvol share, and registers the server as an authoritative identity provider for the domain. Before promotion, it's just a server with a role installed. After promotion, it is a domain controller. When we promote DC01, it will automatically create an AD-integrated DNS zone for corp.dovebridge.tech. AD-integrated zones store DNS data directly inside the Active Directory database, which means they replicate automatically between domain controllers. No manual zone transfers needed. It also creates a special zone called _msdcs.corp.dovebridge.tech, which holds all the SRV records that allow clients and other domain controllers to find services across the domain. Before promoting DC01, we set its DNS to point at its own static addresses, no loopback. Our domain controllers have static addresses that never change, which means there is no scenario where a loopback CAD-address adds value. And there are good reasons to leave it out entirely, not just one. If the DNS server service crashes or fails to start, the loopback address is still reachable because the network stack responds regardless. Depending on the failure mode, the domain controller can appear to have working DNS while returning no useful answers whatsoever. The failure becomes invisible, and invisible failures are the hardest kind to diagnose. There are other problems too. When a domain controller starts up, the netlogon service registers its SRV records in DNS against the server's real IP addresses. With loopback in the picture, that registration process can behave inconsistently. Records may not register correctly or may register against the wrong interface. Microsoft's own diagnostic tool, dcdiag, will flag loopback as a primary DNS entry as a best practice violation, which means your health check reports will have noise in them from day one. And when something does go wrong and you are running nltest trying to figure out which DNS server answered a query, loopback in the configuration is just another variable obscuring what is actually happening on the wire. The pattern here is consistent. Loopback as a DNS entry on a domain controller solves a problem that doesn't really exist in a properly configured environment, and quietly introduces several that do. We are not going near it. Once both domain controllers are promoted and replicating, we make one final adjustment. Each DC adds the other as its tertiary and quaternary DNS entries. So if one controller is ever unavailable, DNS resolution fails over to the other through a real network path. That is genuine redundancy, and it costs nothing to configure. Let's talk a bit more about replication. In a multi-controller environment, Active Directory uses multi-master replication to keep all writable domain controllers synchronized. When you create a user on DC01, that change is replicated to DC02 automatically. When a password is changed through DC02, that change propagates to DC01. No single domain controller is the sole authority. Changes can be made on any writable DC and they'll reach the others. Replication within a site, what we call intra-site replication, happens quickly and automatically. Active Directory triggers replication within seconds of detecting a change, using a process called the knowledge consistency checker to build an efficient replication topology. Within the DoveBridge site, DC01 and DC02 will replicate with each other rapidly. Inter-site replication, between DoveBridge and Rotterdam, is different. It's governed by site links, which define the cost and schedule of replication between sites. We'll configure that when we deploy the Rotterdam domain controllers. Let's talk quickly about diagnostic tools when things don't work. The key tool for checking replication health is repadmin. We'll use it at the end of this episode to verify that DC01 and DC02 are replicating correctly. Alongside that, dcdiag runs a full health check against a domain controller, DNS registration, SYSVOL, Kerberos, FSMO roles, and gives you a clear pass or fail per test. And netdom query FSMO confirms which domain controller holds each of the 5 FSMO roles after promotion. We'll cover all of these tools in depth later in the course. For now, just know they exist and that we'll be running them before we close out this episode. When a user logs into a domain-joined machine, Active Directory needs to verify their identity. It does this using a protocol called Kerberos, the default authentication protocol for Active Directory since Windows 2000 and still the standard today. Kerberos is built around tickets rather than passwords. When a user logs in, the domain controller issues a ticket granting ticket, a TGT. Think of it as a temporary proof of identity, encrypted and signed using a key derived from the TGT account, a special built-in account whose password is the master signing key for every TGT in the domain. The client holds on to this TGT and presents it whenever it needs access to a resource. The domain controller verifies the TGT and issues a service ticket for that specific resource. The resource checks the service ticket and grants access. The user's password never travels across the network at any point in this exchange. The TGT account is one of the most security-critical objects in your domain. If an attacker ever obtains its password hash, they can forge TGTs from scratch for any user, with any privileges at any time, without ever touching a domain controller. This is known as a golden ticket attack. The only recovery is resetting the TGT password twice with replication time in between to invalidate every ticket signed with the old key. Active Directory also supports NTLM, an older challenge response authentication protocol kept for backward compatibility. In 2026, NTLM should be treated as a legacy fallback only. It is weaker than Kerberos. Inside the domain, we organize objects using organizational units, OUs. An OU is a container. You can put users, computers, groups, and other OUs inside it. The OU structure you design should mirror the organization's structure in whatever way makes administering it easiest. And that usually means reflecting either the geographic layout, the departmental layout, or both. For DoveBridge, we'll create OUs for Duivendrecht and Rotterdam, and within those, sub-OUs for departments like IT, engineering, HR, and so on. Here's something that trips up a lot of people. OUs are not security boundaries. You cannot grant or deny access to a resource based on which OU a user is in. OUs serve two purposes. They give you a place to apply group policy selectively, and they let you delegate administrative control to specific people over specific parts of the directory. That's it. The thing that does control access to resources is groups, specifically security groups, which brings us to our next topic. In Active Directory, there are two types of groups, security groups and distribution groups. Distribution groups are used for email. They're not security principles like you can't assign file permissions to them. If you send an email to the entire engineering team, a distribution group is handling that routing. They exist for communication, not access control. Security groups are what we use for infrastructure. They are security principles. You can assign permissions to them, apply group policy through them, and control access to every kind of resource using them. All of our infrastructure work at DoveBridge uses security groups exclusively. Now, within security groups, there are 3 scopes that define who can be a member and where the group can be used. Domain local groups can contain members from anywhere in the forest, but you can only use them to assign permissions within the domain where they live. These are the groups we put directly on resources, the groups whose names appear in the ACL on a file share. Global groups can only contain members from the same domain, but can be used anywhere in the forest. These are the groups that represent logical collections of users: your engineering team, your HR department, your Rotterdam IT staff. Universal groups can contain members from anywhere in the forest and can be used anywhere. They're most useful in multi-domain forests. For DoveBridge, we'll rarely need them. This brings us to the permission model we use throughout this course. AGDLP. Accounts into global groups into domain local groups onto permissions. In practice, Peter.Koster is a member of GG-DUIV-engineering. That global group is nested inside dl-fs-engineering-rw. That domain local group is assigned the read/write permission on the engineering file share. When a new engineer joins DoveBridge, you add them to gg-duiv-engineering, and they automatically inherit every permission that group carries. When you want to add a new resource permission for the whole engineering team, you modify the domain local group, not the individual users, not the share ACLs. It scales, it's auditable, and it stays consistent no matter how large the environment grows. Let's talk about users. More precise, actually, let's talk about objects. Everything in Active Directory is an object. Users, computers, groups, OUS, printers, shared folders. Every object has attributes, properties that describe what it is and how it behaves. User accounts represent people. When Anna Diven logs in, Active Directory looks up her user object and uses its attributes to verify her identity and determine her access. Two attributes are worth knowing by name. The first is the UPN, user principal name. For Anna, that is anna.duiven@dovebridge.tech. This is what she types at the login screen. The second is the SAM account name, anna.duiven. This is the account name Windows uses internally, and what older applications rely on. Combined with the NetBIOS domain name, it becomes corp.anna.duiven. The down-level format you will still see regularly in event logs, Windows dialogues, and legacy applications. Computer accounts represent domain-joined machines. Each has its own automatically managed password and its own domain identity. They are what allow group policy to apply to machines and Kerberos to authenticate machine-level services. If a computer account goes stale, users will see the familiar error. The trust relationship between this workstation and the primary domain failed, something every AD administrator encounters eventually. Groups contain other objects, users, computers, or other groups, and exist to make permission management scalable. Assign access to the group, manage membership, done. We covered scopes and types already. Organizational units are container objects that hold other objects. They are not security principles. You cannot assign permissions to an OU. Their purpose is group policy targeting and administrative delegation. Service accounts are user-like objects created for applications and services rather than people. For anything new in 2026, use Group-Managed Service Accounts, GMSAs, where Active Directory manages and rotates the password automatically. Finally, the Security Identifier, or SID. Every security principal gets a unique SID at creation. Windows uses SIDs, not usernames, to track identity and enforce permissions internally. This is why renaming an account preserves permissions, but deleting and recreating it with the same name does not. The new account gets a new SID, and the old access control entries no longer apply. It's time to talk about group policy. It is one of the most powerful features of Active Directory. A group policy object, or GPO, is a collection of configuration settings that you define once and Active Directory applies automatically to the users and computers in your environment. Security settings, software installation instructions, drive mappings, desktop configurations, login scripts, firewall rules, almost anything you'd want to configure consistently across a fleet of machines can be expressed as a GPO setting. GPOs are linked to containers, domains, sites, or OUS. When a user logs in or a computer starts up, Windows collects every GPO that applies to that object and applies them in a specific order: local, site, domain, OU, known as LSDOU. Settings applied later in the chain override settings applied earlier. There are two exceptions to this. First, inheritance blocking. An OU administrator can block GPOs from higher in the chain from flowing down into their OU. Second, and more powerful, is enforced. A GPO marked as enforced cannot be blocked by inheritance blocking anywhere below it. It wins regardless. Enforced is how you push domain-wide baselines that no department administrator can accidentally or deliberately circumvent. This means you can apply a baseline security policy at the domain level, applying to every computer in corp.dovebridge.tech. and then layer more specific settings at the OU level for particular departments or locations. Rotterdam branch machines might get a specific power policy. The engineering OU might get a different set of startup scripts. All of it flows automatically without touching individual machines. GPOs are stored in two places. The group policy container lives in Active Directory itself and holds metadata: the GPO's name, its unique identifier, its version number, and its links. The group policy template lives in sysvol and holds the actual settings, the configuration files, scripts, and templates that get applied to users and computers. Both halves must be present and in sync for a GPO to apply correctly. SYSVOL is a special shared folder that exists on every domain controller and is replicated between them automatically. Alongside sysvol sits the netlogon share, a separate share that points to the script subfolder inside sysvol and is used by domain join machines to retrieve and run logon scripts during authentication. Healthy sysvol replication is essential. If sysvol breaks, group policy breaks, and logon scripts stop running. It is one of the first things to check when users report inconsistent policy application across the environment. That is everything you need to know about Active Directory before we start building. We have covered a lot of ground, and from LDAP, the directory model, through forests, domains, domain controllers, OUs, users, groups, group policy, DNS, replication, and Kerberos. It is a lot to take in, but you will see all of it come to life in the next steps. Good job. Now we switch to the Hyper-V lab. Our first task is nl-duiv-dc01, a freshly provisioned Windows Server 2022 virtual machine sitting on the DoveBridge network with no domain, no DNS, and no identity infrastructure of any kind. By the time we are done with this server, corp.dovebridge.tech will exist. Let's go. Before we create the actual virtual machine for DC01, we will create a new differencing VHDX virtual hard disk. This new disk will use the master image of Windows Server 2022 data center with the desktop experience. The new disk will only contain changes. It will leave the original master disk alone. In order to make our lives easier, we will make a template disk out of it which we can easily copy for other VMs as we progress through the course. Let's give it an appropriate name. Let's point to our master image VHD. Great. We can now copy our new template VHD endlessly for new VMs. Let's copy the VHD for our first domain controller. Make a new directory with the machine's name to keep things clean and tidy from here. Make a copy of the new differencing VHD and paste it in our new directory. Then, rename the disk appropriately. We can now continue. Let's create a new VM with comparable settings we used before. Of course, name it nl-duiv-dc01. Always give a server with the desktop experience installed 4 GB of RAM. Be generous. Connect the network adapter to the DoveBridge's first local area network. Select the VHD we created. Let's change some settings. Give it 4 virtual processors and change the snapshot settings. Before we start the VM, let's make a snapshot so we can always revert back to the state where we haven't started it yet. Great, let's go. Let's change some settings in the OOBE. I recommend you to change the preferred application language to English United States. Change the keyboard if necessary. When signed in, give the machine one single reboot. Make a snapshot of the VM. First, let's change our IP version 4 settings. I'm done working within a small window like this. Let's enable remote desktop and sign in remotely. That really does make a difference. We are almost about to install Active Directory domain services. But first, let's change the network settings of this server. We will keep it easy for this server by using the graphical interface. We already configured IP version 4 for this future DC, but nevertheless, let's open its settings and temporarily set the loopback address as the secondary DNS server. Now go to the settings for IP version 6. Enter in the IP address for this server. This will be FD501011010 with host ID 11. With IPv6, the default gateway is set automatically because the protocol uses router advertisements to configure network settings dynamically. Leave it blank. For the secondary DNS, again, use a loopback address temporarily. Now, we must change the name of the server. After the required reboot, we are ready to install and configure Active Directory domain services. Let's install Active Directory domain services. We'll use the Server Manager for both installing and configuring Active Directory on this server. You can also easily install it using PowerShell, but we will not do that for this course. However, I will show you what promoting this server would look like using the CLI. Let's go to the Server Manager. Add roles and features. Select both Active Directory domain services and DNS. We can now promote this server to a domain controller. Also notice the warning sign at the upper right corner. We are creating a new forest. Name it corp.dovebridge.tech. Do not change the forest and domain functional level. The AD restore mode password is a special password used to boot Active Directory domain controllers in recovery mode. It allows administrators to perform tasks like restoring or repairing Active Directory data. We will set the NetBIOS name to corp, which is short for corporation. Leave the defaults. As promised, I will show you how to do the exact same thing as we're doing in this graphical wizard in PowerShell with a single command. The wizard will offer you to review and save the script for later use. We are now promoting the domain controller. When the promotion has finished, the server will reboot automatically. The server restarted. It is now the first domain controller on the network. Let's change the user account RDP uses. Let's sign in with the AD Integrated Administrator account. Then, let's connect to the server. And we're in! Amazing! It's default behavior that the promotion process will set the DNS client to loopback addresses. That's normal, but we need to change these settings back. Set the secondary DNS address to the address of our second domain controller. DC02 will receive host ID 12. In the IPv6 config window, click Advanced. Then click the DNS tab. Disable automatically registering the server's IPv6 addresses automatically in Active Directory. We are doing this because the server will often receive a new dynamic IPv6 address. By changing this setting, we prevent the server from polluting DNS records into our zone. Let's check if everything went well. Let's do a first sanity check. Let's open the CLI and run getAD domain. Then run getAD forest. This confirms the domain name, NetBIOS name, functional levels, and forest root are all correct. It looks good to me. Now let's check if all FSMO roles are available on this first domain controller. Yep, this looks great. Let's talk about FSMO roles. Active Directory lets any writable domain controller accept changes. But 5 specific operations need a single authority to avoid conflicts. These are the FSMO roles. 2 live at forest level. The schema master controls schema changes, and the domain naming master controls adding or removing domains. 3 live at domain level. The RID master issues unique identifier blocks to other DCs, the infrastructure master maintains cross-domain object references, and the PDC emulator, the busiest, handles password changes, lockouts, group policy updates, and time synchronization. When DC01 is promoted as the first domain controller, it receives all 5 roles automatically. When DC02 joins, nothing changes. DC02 becomes a full replica and shares the authentication and DNS workload, but FSMO roles stay on DC01 unless you deliberately move them. And no, 2 domain controllers cannot share the same role. Each role has exactly 1 holder at any given time. That is the entire point. In most environments, you rarely need to transfer roles. A reboot or short maintenance window does not justify it. DC02 covers authentication and DNS seamlessly, while DC01 is briefly offline. Where transfer makes sense is in mission-critical environments where even a 10-minute outage has business impact, or before permanently decommissioning a domain controller. In both cases, the PDC emulator is the role most worth moving first. FSMO roles do not transfer automatically when a DC goes offline unexpectedly. They are simply unavailable until that DC returns. In a permanent failure, you can forcibly seize a role on another DC. But once you seize, the original DC must never return to the domain. It still believes it holds the role, and reintroducing it causes exactly the conflicts the FSMO model exists to prevent. For DoveBridge, all 5 roles sit on DC01. That is correct, expected, and requires no further action. Anyhow, I am satisfied with the results shown to me. Let's open up the DNSMMC snap-in. Open the forward lookup zone for corp.dovebridge.tech. You will notice that the server has automatically registered its global unicast IPv6 addresses in the zone, exactly as we discussed earlier. We are going to remove those now, because if we don't, promoting the future second domain controller will fail. You will also find the address in the following 2 zones: domain DNS zones and forest DNS zones. Remove the address. And the _MSDCSGC zone, remove the address as well. Now we need to make sure this server only listens to traffic on the static IP addresses we defined. Apply. Next, let's define public DNS resolvers for the server it can forward traffic to when it does not own the DNS zone for the query. We could have used our own ISP's servers, but let's use the Cloud9 servers for this course. They seem to be doing a good job hosting them. With our forward lookup zone in place, there is one more DNS component worth configuring before we move on. Let me tell you about reverse lookup zones, and to make it concrete, we are going to follow an email. Imagine Anna Duiven hits send on an email to an external contact. Her mail server delivers it to the recipient's mail server somewhere on the internet. But the receiving mail server does not just accept the connection blindly. Before letting anything through, it wants to verify that the server knocking on its door is who it claims to be. It knows the IP address of the connection. What it does not know is whether that address belongs to a legitimate mail server for DoveBridge. So it asks its DNS resolver, given this IP address, what hostname does it belong to? This is a reverse lookup. In normal DNS, you start with a name and get back an address. A reverse lookup does the opposite. You start with an address and get back a name. The record that holds this mapping is called a PTR record. To fit inside the standard DNS tree, the IP address is reversed and expressed as a name under _adr.arpa for IPv4 or IP6.arpa for IPv6. The resolver walks the DNS tree, following delegations until it reaches the authoritative server that holds the PTR record and returns a hostname. The receiving mail server then does one final check. It looks up that hostname the normal way and confirms it resolves back to the same IP address. The address and hostname agree. This is called forward confirmed reverse DNS, and it is the handshake that confirms legitimacy. Anna's email goes through. A spammer trying the same thing has no matching PTR record or one that does not check out. The connection is rejected. No PTR record, no trust. The same principle applies internally. When diagnostic tools, health checks, and monitoring systems perform reverse lookups on our domain controllers, they expect PTR records to exist and match. Without them, checks fail and logs fill with raw IP addresses instead of readable hostnames. This is why we create reverse lookup zones for both our IPv4 and IPv6 ranges, AD integrated, replicating automatically between DC01 and DC02, no manual zone transfers needed. Forward lookups resolve names to addresses. Reverse lookups resolve addresses back to names. Both directions work, and every tool that depends on DNS gets the answers it expects. Let's create a reverse lookup zone for IPv4. We will create a primary DNS zone. We will replicate this zone to all domain controllers in this forest. Let's enter our network ID. We're done for IPv4. As you can see, a PTR record is missing for DC01. Let's make it. Browse for the host name. You can find it in the corp.dovebridge.tech forward lookup zone. Now, also add a reverse lookup zone for IP version 6. We will be using pretty much the same configuration. We will be using FD 50101010 with a 64-bit subnet mask as the prefix. Again, add the pointer record. We finished installing our first domain controller. Now it's time to add a second DC to the domain. Again, create a differencing VHD, make the server core installation its parent. Name it nl-duiv-dc02 and connect it to the network. Give it 2 GB of RAM and 2 virtual processors. Make a snapshot of the VM. Let's change the name of this server to dc-duiv-dc02. Yes, reboot. Before installing Active Directory domain services, let's change the network settings. As you can see, our OPNsense router gave the machine proper addressing. However, of course, DC02 requires static IP addressing. First, remove the current IPv4 address from the adapter. Great. Let's set the static IPv4 address now. Nice. Now let's set the static IPv6 address for the server. Great. Almost there. Remember how DC01 polluted our DNS zones with its GUA address? We're going to prevent that from happening again for our second domain controller. This is very important to do. The promotion of DC02 will fail if you don't disable this behavior. We are now totally ready for making this server a member server, but joining the domain. The easiest way of joining is by using the sconfig tool. Specify the administrator account, enter the password, and reboot without renaming the machine. If joining the domain goes wrong, it's pretty much always caused by wrongly configured network adapters. DNS in particular is the culprit in most cases. Back on DC01, launch the MMC snap-in Active Directory users and computers. As you can see, DC02 has joined the domain successfully. Let's add the newly joined machine to our server manager so we can manage it remotely easier. Great! The machine has been added successfully to the server manager. We are going to install Active Directory domain services on DC02 right now and then promote it to a domain controller. We will do that with the graphical server manager for this course, but just for fun, let me show you how to do it using PowerShell. We have successfully installed ADDS. The machine will reboot. We're not actually going to run this. Let's move back to the server manager on DC01. Let's promote the machine using the server manager wizard. Replicate from any domain controller. If you click the drop-down, you will only find DC01 there. As I showed you before, you can also find the PowerShell script the wizard is running under the hood that promotes our member server to a domain controller. Great, let's promote this server. The promotion was a success. Let me open Active Directory users and computers. You will notice that DC02 has moved from the computer organizational unit to domain controllers. In the DNS management tool, you will see all DNS records are correctly present, as they should. To verify that the promotion was 100% successful and that the Active Directory is healthy, let me run some diagnostic tools. Let's start with the replication admin command with the summary parameter. This will give us a high-level overview of replication health across all partners. Start here. 0 failures is what you want. No errors, so I can proceed. Let's check if the replication queue is hanging. It's not, but let's check nonetheless. Let's do a comprehensive health check in verbose mode. It runs on both DCs individually. Let me speed up the video for a moment. It looks good to me. Let's do a full DNS health check now. It verifies SRV record registration, dynamic updates, and name resolution. Great. That is a wrap on Active Directory domain services. We covered a lot of ground in this episode. We started with the fundamentals, what a directory service is, where LDAP fits in, and how Microsoft built Active Directory on top of it. We walked through forests, domains, organizational units, users, groups, group policy, DNS, replication, Kerberos, and the FSMO roles that keep the whole system running. Then we got our hands dirty. We prepared DC01, promoted it, created the corp.dovebridge.tech domain from scratch, and watched it come to life. We built DC02 on server core, promoted it, and verified that replication, DNS, and every health check came back clean. Take a moment to appreciate where we are. We started this course with nothing but a Hyper-V host and a network diagram. Now we have a working enterprise domain, 2 domain controllers, fully replicated, dual stack serving DNS, issuing Kerberos tickets, and ready to authenticate every user and machine we throw at them. This is the foundation that everything else in this course builds on. File services, DFS namespaces, branch cache, the Rotterdam branch, group policy hardening. All of it depends on the infrastructure we just built. Every lesson from here forward will feel faster and more connected because the identity layer is in place. In the next episode, we build out the OU structure for DoveBridge, create our user accounts, and establish the security groups that will govern access to every resource in the environment. See you there in Part 7.